Hi, I'm Brandon, and this is my presentation on a paper on directed Greybox fuzzing. So, have you ever had this happen to you, where you're using a program normally as you would expect to use it, and suddenly it crashes on you? Well, as a user, this can be incredibly frustrating, but as a developer, this can be even more frustrating as the software that you've written suddenly is crashing on people. And that's kind of the main motivation behind this paper and the technique discussed in it, and that is fuzzing. So in modern software, in software in general, vulnerabilities and bugs can be difficult to find, and this is where fuzzing has been created. And fuzzing is essentially taking or finding inputs for a program that will cause unexpected behavior, like crashes. Um, and this can be difficult nowadays because modern programs are huge. They can be they can be thousands and thousands of lines long, and finding that input that crashes the program can be really difficult. So there's three main approaches to fuzzing. The first one is one that we're not really going to talk about, and that's black box fuzzing, and that's essentially just throwing inputs at a target and looking at the output and not really doing anything based on that. But the other two approaches that we will be talking about are gray box fuzzing and white box fuzzing. So gray box fuzzing is what we've been working with for this capstone. Essentially, you are still taking inputs and throwing them at a binary, but there's more complexity to it than that. So essentially, you'll take seed inputs, or you could start from nothing as well. But you'll take those inputs and you'll take an input and you'll mutate it. So you'll change something about that input, and then you'll pass that along to the binary. And in gray box fuzzing, you will have some way to gain information about the binary by instrumenting it. So what we've done and what modern fuzzers do is look at code coverage. So when the code is, or when you're preparing the binary to be fuzzed, you put something in it that shows you like when you're covering certain parts of the binary, and that information can then be sent back to the fuzzer, and then it can choose to do what it wants with this information. In our case, when an input increases coverage of the binary, it's then put into a pool of inputs that it will then go through to further mutate and test those mutations as well. And this is really advantageous because it allows for you to do tons of executions of the binary in a really short period of time. And this means that uh, you can really effectively test out different branches uh, of a binary in order to reach a crash-inducing input. However, this comes with the limitation that it is dumb, so to speak. So although the fuzzer has knowledge of something like the coverage of the code, it doesn't have any other knowledge of the structure of the code. So it can struggle with things that can be more complex. And an example of a modern gray box fuzzer is AFL, and that's uh, the current fuzzer that the paper tests its fuzzer against. Um, the next fuzzer, or the next method of fuzzing is white box fuzzing. And for the most part, most white box fuzzing is done, or most white box fuzzers are directed. And this means that they have a specific target that they are attempting to reach within the program that they're working towards achieving. And so in white box fuzzing, they do what's called symbolic execution. So instead of gray box fuzzing, where you have a fully compiled binary, with white box fuzzing, you'll have the code itself or some representation of it, like uh, some like machine code representation of it. And what the white box fuzzer will do is it will try and calculate the best route in order to get to the target locations in the code. And maybe you're wondering you may be wondering what's the drawback of doing that, and that's that this technique is extremely slow. In the time that it takes for a white box fuzzer to generate even one input to test with the program or to use for the program, a gray box fuzzer could generate thousands upon thousands of potential executions that could have uncovered the crash-inducing input first. And a white box fuzzer that's currently state-of-the-art that's being used is Catch, which is based on Cree, and that's what AFL Go, or that's what the fuzzer in this paper was tested against. So in order to illustrate the limitations of these fuzzing techniques, we're going to talk about Heartbleed, the Heartbleed vulnerability. So this was a vulnerability within the Open SSL library. So what it essentially allowed you to do was in TLS, when a connection has been established, you can do what's called a heartbeat to make sure that a connection is still alive. The client can tell a server, hey, here is this code, here's how long this code is, and the server will then send back that code to the client, and if the code matches, then the client will know that the connection is still alive. But what you could do with this vulnerability is the client could say, here is a 1 byte message, and then send a 64 kilobyte message. The server would receive that message, they'd copy back the first byte correctly, and then they would dump the next 64 kilobytes, whatever was written in memory. And so this vulnerability was pretty serious, and it was introduced in this small patch here, just these few lines of code mainly. And as you can imagine, OpenSSL is a huge library. So if you were to try and fuzz this with a Greybox fuzzer, it would take a ton of time for each iteration of the fuzzer. Yeah. Looking at, as I just talked about, looking at a Greybox approach, you would fuzz the entire library, each iteration of the fuzzer, and you may or may not hit the vulnerability. The fuzzer might get onto a certain branch and continue executing inputs that continue on that branch, and that branch could be completely separate from where this vulnerability is, and you would have no way of directing the fuzzer to get to this point. Looking at a white box approach, you could target the patch, so you could set the white box fuzzer to try and get to this point in the code, and you would go through with symbolic execution and try to solve for the correct input that would bring you to this point in the code. But as you can imagine, I mean, you can see this is line 1400. This would take an incredibly long amount of time in order to get to this point. So the solution proposed in this paper is directed Greybox fuzzing. So what this essentially does is you're taking a Greybox fuzzer and you're giving it a target. So you'd still be mutating inputs, and this would mean that you're executing the binary repeatedly, but this time you're actually working towards a target in the code. And in this paper, they created what they call AFL Go. So this is built off of AFL. It is able to target code blocks in the binary, and it comes with the benefits of Greybox fuzzing, with being able to run the code thousands and thousands of times in a short period of time. So before you get scared of this graph, it's really pretty simple. If you in our capstone, when we worked with our instrumenting our binaries and working with our fuzzers, this is pretty much that with a few extra steps beforehand and during. So just talking about the instrumentation of the binary, when AFL Go takes the binary, it extracts the call graph and the basic block control flow graph. So this image on the left here is what the call graph would look like, and that's basically the flow of the program between the different functions in the program. And the control flow graph on the right here shows how the program flows between the different blocks of the program as opposed to the functions. And using these two graphs, the AFL Go will then calculate the distance from the seed from each point in the binary, and it does this on the function level using that call graph, and the basic block level using the control flow graph. It'll then take that information and add that on to the AFL instrumentation, and the added instrumentation is not that much more code than what is already there. And because of the way it's set up, most of the program analysis is done in this instrumentation step here, as opposed to at runtime, like a white box fuzzer would be doing it. And the next major addition that AFL-Go makes to AFL is using what they call simulated annealing. So this is based on a metallurgic process, which is where they'll take a material and they'll heat it up and cool it down repeatedly. And this is done in order to strengthen the material, remove impurities, and increase crystal size in that material. And as you can imagine, that's how it works. That's how it works in this program. Looking at the graph, it's a good way to visualize it. The algorithm will take some inputs that are worse that are worse, that aren't as good as getting close to the target. But this is all in order to approach the target better. And as time goes on, the amount how worse the input is slowly decreases over time, and this is done through the temperature parameter. So although it will be accepting worse inputs, how bad the inputs are is slowly waned off as you approach the target location in the code. And then, yeah, so with AFL-Go, they had a few tests in order to benchmark how good it was. So one of the applications they used was patch coverage. So what they did was they took a couple of different libraries and that had patches to them, and they compared AFL-Go against Catch, which is the white box fuzzer. So when they ran both fuzzers, and they found that AFL-Go, as you can see from the graph, was able to cover a higher number of targets as compared to Catch. However, as you can see, because it is a Venn diagram, there are targets that Catch was able to cover that AFL-Go was not able to cover. And this can likely be attributed to the fact that because white box fuzzing is better suited for finding finding areas of the code that require more complex conditions, they're able to find those targets more easily than AFL-Go, which would struggle to get into those areas, or as they call them, compartments. The next application of AFL-Go that they used was continuous fuzzing. So what they did was they took Google's OSS Fuzz platform, and this is essentially a platform where they'll take open source projects and they will continuously fuzz them, and they can do somewhere around like trillions of executions per day. And as you can imagine, software that has been run through this platform has been fuzzed significantly, and they found that when they integrated AFL-Go within Google's platform, they were able to make 26 reports of bugs, and 10 of them were assigned CVEs. The last application of AFL-Go that they used was crash reproduction. So as I showed at the beginning, when a crash happens on your computer, you don't really want to send all the information of what's on the user's system, because this is a huge privacy concern. So instead, you want to send the stack trace of the program, which is what it dumps when it fails, and that's why you should click those report this crash button when it pops up. But what they do is they take that error within the stack trace and they set it as a target to pass on to the fuzzer, and then see if the fuzzer is able to recreate that crash. A software that currently exists to try and attempt this is Bug Redux. So when they ran a test to find all of these different crashes against Bug Redux, they found that AFL-Go was able to find almost all of the crashes, except for one, which was attributed to the fact that it required 2 files as input, and AFLGO was only engineered and written to provide one file. So likely they would have been able to find that crash had it been written to do this test better. So as we can see from this paper and the tests that they conducted, Greybox fuzzing is a really effective method of fuzzing. It is able to leverage its advantages over current software that exists, such as AFL or Catch, combining the strengths of standard Greybox fuzzing with the targeted fuzzing of with the targeting of white box fuzzing. And it works in all of the different applications like patch testing, continuous fuzzing, and crash rate reduction. There are some limitations to the technique. As I had mentioned within the patch testing, directed Greybox fuzzing really struggles when you're working with more complex branches, just because there can be really specific requirements that the input needs to have, and just mutating an input over and over again to try and get through those requirements can be quite limited when compared to something like a white box fuzzer that could mathematically solve what the input should be. Additionally, as with our fuzzers and normal Greybox fuzzers, it is still reliant on how good it can be reliant on how good your seed inputs are. So if you have seeds that are another limitation is that Greybox fuzzing is reliant on seed inputs. The seeds and how effective they are at increasing coverage and approaching targets can have a big impact on how your code is able to find those targets. And lastly, the code can still miss bugs, as demonstrated with its comparison with Catch. So what can we take away from this paper? Well, as the paper has demonstrated, Greybox fuzzing is a technique that is definitely worth investing more time and research into. It is able to work better than a lot of current existing software, and it works well within existing systems. Some of the some potential future work that was mentioned in the paper was integration with white box fuzzing techniques, and this would mean that the fuzzer would have more knowledge of what or of the source code of what it is fuzzing, and this would allow it to find things that require more complexity, combining the strengths from white box fuzzing with the strengths of Greybox fuzzing.